Hello everyone, welcome back. So today we are going to solve a problem called magic index. So what does magic index means? So let me just explain you what does magic index means. So I will be called a magic index in an array of a if a of I is equals to I. This means what? The index and the value of index is same. So this is a problem from this book, Cracking the Coding Interview, and this is in the recursion chapter. So let me give you an example to make you understand better what this problem actually saying. Like we have this array called A. So here we have all the elements and I have also written down the index values of the elements. So the magic index will be a index where the index value and the value at the index are same. Like for this example here 7, the value at index 7 is 7, so that's why the index 7 is called the magic index. So we have to find this. So the constants given are the array which is given should be sorted. So this is number one constraint. So the array should be sorted. The next constraint is all distinct integers. The array should consist of only all distinct integers so that no two integer is same in this array. So this is the second constraint. So first of all, this may seem a very simple problem, like if you do it in brute force way. So what the brute force approach would look like looping through all the elements from 0 to length of the array and check if I is equals to a of I, where a is the array. Then if it's true, return the I. So it will be order of n solution, but we have to do it faster. So how can we do it faster? So let me just focus on these constraints again. So here it says it is a sorted array. So whenever we come across the term sorted, the immediate algorithm which should come into our mind is binary search. So binary search. So here we have to understand how we can use binary search for this example. So let me just tell you how binary search works. So for binary search, we first find out the middle element. So for this example, this is of length 0 to 10, that means 11. So 11 by 2 is what? 5. If we take the float value, so come here 5. So at index 5 we have value 3. So it is not the same. So that's why we don't check it here. So after that we have two separate parts, one at the left part, one is at the right part. So we have to only check only one part. So how to know which part to check? Now very carefully listen. At index 5 we have the value 3, which is what? Less than the value at the index. So 3 is less than 5. So we have to make it what? We have to make it equal to the index. So that's why we have to increase this value. So for increasing values, we don't need to check the left part because we know all the values at the left of 3 would be less than 3. So that's why we only check the right part. So again, we will find the middle at the right part from here to here. So what would be the middle? The middle would be this element. So here 8. At index 8 we have more than 8, 9. So which means what? We have to decrease 9. So we will again check in the left part. So after checking this left part, we will again check the middle element. The middle element here becomes this. So now here what? The index value and the value at the index becomes same. So we will return what? The index of the value, which is 7. So we get our answer. So this is how the binary search comes into consideration for this example. So what will be the time complexity for this solution? The time complexity will be same as binary search, which is log n, which is significantly less than order of n. So this is how we solve the magic index problem. So now here comes a twist. If let's suppose we don't get this constraint, the second one, all distinct integers, we get something like non-distinct elements also. Like for this example, minus 10, minus 5, 2, 2, 2, 2, 3. Here we have repetition of elements. If we here we check what is the magic index, we get two magic indexes. Like one is this one, 2 and 2, one is this one, 7 and 7. So how to deal with this type of problems where there are not explicitly saying that there will be only distinct elements. So let's see for this example. Now let us see how to solve for this condition where all the elements are not distinct elements. So here we also try to use the algorithm of binary search. First of all, we find the middle element. Here also we have 11 elements, so the middle element would be 5. So this is not same. According to the previous logic, what we have done is, if this value is smaller than this value, then what we have done, we only check the right part. But here the twist is, here can be that somewhat like the magic index can be present at the left side also, which is indeed true for this example. Like the magic index is present at the left part, so we have to check the left part also. So now if we check the left part, we go to the previous index. The previous index is what? 4. Here we see at 4 we have the value of 2, so which is also less. So we don't need to check this value, because at 5 we have the value 3. So which means at the immediate left we at least want to have what? The value which is equal to 4, but 4 is greater than 3, so it cannot be left of, I mean, 3. You are getting my point, right? Because it's a sorted array, right? It has duplicate elements, but it is a sorted array. So at the index of 5, it is having what? 3. So at the index of 4, to make it a magic index, it should have at least what? 4 value. So this 4 is what? Greater than 3. So 4 is greater than 3, so that means at 5 if we have 3, at 4 there is no possibilities of having 4, because 4 is greater than 3. 4 should always be at the right of 3, so we don't need to check the fourth index. So that's why we will use this technique. Here we will find from where we need to check in the left. We will find the minimum of middle minus 1 comma middle value. So middle minus 1 is what? Middle minus 1 is 4. We will find what is the minimum between this 4 and this value 3. Here the value 3 is minimum, so that's why we will start checking from this index 3 from here, because at 4 there is no possibilities that we will have 4, because 4 is greater than 3. You get my point, right? So from here we will check. So from here we will checking again. We will do the binary search way. 1 2 3 4 elements, so 4 by 2 2. So this is the middle element. Here we find the magic index, we will return the value 2. Now after understanding the left part, we will now look at the right part. If suppose the magic index is not present in the left, so we have to find it in the right. So we will do the same procedure. Instead, here for right index we will see which is the maximum of mid plus 1, which means 6, and mid value. So mid plus 1 is what? Mid, here it was 3, sorry. Mid plus 1 is 6 and mid value is 3, so maximum is 6. So we have to start checking from this element itself. So these are the logic. So let me just write the code for these two problems and let me just go through it. So here also the time complexity would be order of log n.
Now let's look at the code for the two solution I have just mentioned. So this is the solution for the case where only distinct elements are possible in the array. So here we have taken this input, and first of all we will finding out the length of this array and passing it through the magic index function, this array, and the size. So let's see, this magic index function will be calling a recursive function called helper. So here we are passing what? The array itself, the index 0, and the size -1. So what this 0 is, the 0 is the value, or rather the 0 is the start index, and the end is start -1. So these two we are passing. So now in the helper function, what we are doing, we are checking if end is less than start. That means what? We have traversed through whole array and we haven't find out the element, so that's why we're returning -1. Then we are finding out the middle element. This is exactly the same thing what we are we are used to of doing in the binary search. So here we are checking if the middle element and the middle index is same, then we will return middle, and else if middle element is greater than the middle, then the end becomes mid -1, and else the start becomes mid +1. So let me just run through it. Run script. Here it is giving output 7, so which is indeed true, this 7. So now let's check out the condition where it is the repetitions are allowed. Here the repetitions are allowed, which is almost similar. Here also we have a recursive function, and this condition is exactly the same as the previous one. The main difference is here we are checking the left index, which is the value of minimum mid index minus 1 and mid value, which I have just discussed in the whiteboard, and then we are calling the helper function from start to the end, now being the left index, because we are skipping some values because we don't want to check them, and we don't want to check them because we know that these values cannot be a magic index. So that's why we are skipping some values and finding the exact index from which we have to check. So this is why the left index is used here, and here also right index, which will be max of mid index plus 1 plus mid value, and the rest of the part is exactly the same as the previous solution. So let me also run this. Here we are getting the output 2, which is also correct because 0 1 2 2. Here it is the magic index. So the solutions link will be at the description box below. Another announcement I want to do is, like, I will be making a playlist called Algorithm 101, where I will be telling you about some nitty-gritty techniques and how to optimize a solution, how to calculate time and space complexity. So I will be very soon coming up with an algorithm series. So do follow the channel for more updates. Thank you for watching.